Our today's topic is solving differential equations using the integrating factor method. So in this lesson, we'll learn how to solve first order linear differential equations using the integrating factor method. Because this method helps convert a differential equation into a form that is easy to integrate. There are many differential equations which cannot be solved by separating the variables. So first of all, let's see what is the special kind of first order linear differential equation, or the standard first order linear differential equation can be written like dy by dx plus p of x into y is equal to q of x. That is the standard first order linear differential equation. Why first order? Because if we write it like this, equal to q of x minus p of x, so highest power of the variable is 1, so first order linear differential equation, where px and qx are functions of x, that's an independent variable. So our primary goal is to determine y as an explicit function of x. So for this we have a magic multiplier that is called integrating factor. So we multiply by a magic multiplier that is called integrating factor on both sides, that is equal to I of x, and that's given by e raised to power integration of px respect to x. We don't need the constant of integration at the exponent of e, and then we multiply both sides of equation 1 by integrating factor. So the equation 1 implies dy by dx plus p of x into y is equal to I of x into q of x. And then after multiplying the entire differential equation by integrating factor, turns the left hand side into the derivative of a product, so that will turn like dy by dx of integrating factor with y, that's equal to I of x times q of x. First step is write the equation in standard form, find the integrating factor, multiply the entire equation by the integrating factor, rewrite the left side as a derivative, integrate both sides, and then solve for y. Let's take one interesting example over x divided by x cube. So our example is solve dy by dx plus 3 over x into y is equal to e raised to power x over x cube. Clearly it is a first order linear differential equation of the form dy by dx plus px into y equal to qx. So we need to identify what is px. So px is equal to 3 by x, that will help us to get our magic multiplier, and q of x e raised to power x divided by x cube. So integrating factor e raised to power integration of px, that 3 by x respect to x, so that's equal to e raised to power 3 times ln magnitude of x. We don't need the constant of integration here, so that's equal to e raised to power ln magnitude of x cube, that's equal to x cube. So we multiply equation 1 both sides by x cube, multiply equation 1 both sides by x cube. So therefore equation 1 implies dy by dx, or x cube, into dy by dx plus 3 by x into y into x cube is equal to qx. Qx is e raised to power x divided by x cube times x cube. Cancel the common factors here, x cube, here we get. So therefore now collect the terms, make it as a product of integrating factor. So d by dx x cube into y is equal to e raised to power x. Both left hand side and right hand side are integrable. Now we can apply the product rule and verify also x cube into dy by dx. Then here we are left with 2x square, 3x square into y, so we get the correct answer. Or we can write one more step if we want. So that's equal to, that implies integrate d by dx x cube into y with respect to x, integrate e raised to power x with respect to x. So derivative and integration cancels, is equal to e raised to power x plus c, make y as a subject, y is equal to e raised to power x plus c divided by x cube. So that is how we use integrating factor method to solve first order differential equations. Okay, let's solve very interesting past paper question. It was asked in May 2018 HL paper 3. So consider the differential equation, first order linear differential equation. Let's solve one past paper question which was asked in May 2018 HL paper 3. So we have a differential equation of the form x into dy by dx minus y is equal to x raised to p plus 1, where x belongs to real and x cannot be equal to 0 and p is a positive integer, p greater than 1. Given y is equal to negative 1, where x is equal to, solve for y as a function of x. Okay, so let's solve. So first of all, make it of the standard form, dy by dx minus y equal to x raised to power p plus 1. So that implies divide by x on both sides, 1 over x into y is equal to x raised to power p minus 1 plus 1 over x. Now it is of standard form, dy by dx plus p of x into y is equal to q of x. So we can use integrating magic multiplier, integrating factor I of x is equal to e raised to power integration of negative 1 over x to x, that's equal to e raised to power negative ln x, and that's equal to e raised to power ln x raised to negative 1, that is equal to 1 over x. So multiply equation 1 by 1 over x. So 1 over x into dy by dx plus or minus y into 1 over x square is equal to x raised to power, or we can just say 1 over x into x raised to power p minus 1 plus 1 over x, or later we can simplify also, and that is a product of two functions, d by dx y into x, or we can say y into 1 over x is equal to x raised to power p minus 2 plus x raised to power, or we can say 1 over x square after multiplying inside. So now we are in a position to integrate. So integrate both sides. So integrate both sides with respect to x. So y into 1 over x for y over x is equal to into x raised to power p minus 1 minus 1 over x plus constant of integration. So make y as a subject, y is equal to multiply by x, 1 over p minus 1 into x raised to power p minus 1 plus c into x. Now since the point is given, since x is equal to 1 and y is equal to negative 1, so we can solve, find c. So therefore negative 1 is equal to 1 over p minus 1 into 1 raised to power p minus 1 plus c. So we can find c in terms of p. Negative 1 will get cancelled. C is equal to, therefore c is equal to negative 1 over p minus 1 or equal to 1 over 1 minus p. So we can substitute to make y as a subject over here in this equation. So that is x raised to power p over p minus 1 minus 1 minus x over p minus 1. That is how we can solve. However, this question can be solved by using y is equal to vx substitution also. But many times, many questions cannot be solved by substitution or separating the variables. So integrating factor, the magic multiplier, is always helpful in that case. Thank you.